Photoelectron Spectroscopy, a presentation by David Faulds and Sridhar Deshpande. So to begin with, we're going to talk about what photoelectron spectroscopy is and what concept is at the heart of it. So the concept that is central to photoelectron spectroscopy is the photoelectric effect, which suggests that you can use photons of light to knock out electrons from various substances. Essentially, every electron in a substance has a certain binding energy that is caused by electrostatic attraction. This electrostatic attraction is represented through Coulomb's law, which is the product of the charges divided by the radius squared. The radius is the distance between the two different charges. So electrons that are farther away from the nucleus will have less electrostatic attraction than the ones that are closer to the nucleus because their radius is much larger. And so you can use photons that may have greater energy than the binding energy of those electrons and hit the electrons with those photons to knock them out. So this is represented by the equation HV equals KE plus BE. And HV is the energy of the photon, H is Planck's constant, V is the frequency of the light, KE is kinetic energy, and BE is binding energy. And if you have a known value, a known frequency of light, and you can find the kinetic energy through a detector, then you can determine the binding energy of that electron. And the binding energy of that electron is equal to the ionization energy, which is the amount of energy required to remove one electron from the substance.
So just a quick overview of electron shells and why photoelectron spectroscopy works. So we know from the quantum theory of atoms that electrons are arranged in shells in atoms. They're not arranged in sort of continuous distances from the nucleus. There's only a set amount of places they can be. So each shell is composed of subshells, the s, p, d, f, and then those are further divided into orbitals, which hold up to a pair of electrons. So each electron can only exist in a particular amount of specific places within an atom in quantized levels. So this is useful in photoelectron spectroscopy because we know that if we bombard it with a certain energy wavelength of light, it will either knock or not knock out an electron. There's not a continual amount of electrons that will be knocked out. Either it will go or it won't, depending on the amount of energy. So using this, we can calculate the ionization energy needed for certain atoms based on whether a wavelength will displace electrons or not. So in the actual process of photoelectron spectroscopy, what you want to do is you want to ionize your sample into a gaseous state, and you want to do this to avoid intermolecular forces, which will cause errors. So you ionize it into a gas and you place it in your sample chamber here. Then you bombard it with X-rays of a particular wavelength, and what this will do is it'll displace electrons from your sample, and these electrons are captured in the analyzer and they're just bent around into a sensor. And what the sensor will do is it'll take the angular momentum of the electrons that you know, and then you can calculate the kinetic energy through the equation 1/2 Ke equals 1/2 mv squared. So then you will know the kinetic energy of your sample, of the electrons from your sample. So when you know that kinetic energy, you can then calculate the ionization energy, provided that you know the wavelength of the original X-ray you used. And the computer will do that here through the XPS spectrum, which will do the analysis for you, and it'll give you a very nice chart of the amount of electrons displaced versus the energy needed to displace them.
So using photoelectron spectroscopy can tell you a lot about the relationship between orbital energy and ionization energy. We talked about Coulomb's law earlier and how the energy between the electrostatic attraction between electron and the nucleus is inversely proportional to the square of the distance between them. And we know that as an electron gets farther and farther away from the nucleus, it has more energy because it has to essentially fight against the energy that is pulling it towards the nucleus. And however, this level of energy is discrete and it varies from level to level. So here we have potentially a 2p6 level. Here we have a 3s2, 3p6, and a 4s2. So what happens is that as these electrons get farther away, they have less and less ionization energy because by Coulomb's law the electrostatic attraction is less, so they can be knocked out more easily. And this is made more clear through the spectrum analysis of an orbit. So here we have an example of the data that could be spit out from a photoelectron spectroscopic unit. And on the x-axis we have the ionization energy, and as you can see the ionization energy increases from right to left. So essentially here we would have the nucleus, and on the y-axis we have the relative number of electrons going from the least to the most. And what we see here to begin with is a orbital that is going to have a very high ionization energy. In fact, the most out of compared to all the other peaks, which suggests that this is the core electron, as that is where the electrostatic attraction is going to be greatest. And here we see that it has a small peak, and when you move to the next peak, which is about a tenth of that, you get another peak of the same size, which shows that at both of these ionization energies, you have approximately the same number of electrons being released. And we know that the smallest subshell is the S shell, and in the S shell you have one orbital that contains 2 electrons, and so thus we can determine that this is the 1s2, and this is going to be your 2s2. Looking at the next peak, which has only a slightly higher ionization energy, we see that the peak is about 3 times as tall, which means if this has 1 orbital, this is going to have 3 orbitals, containing 6 electrons total. And from that we can determine that this is the 2p6. We know that this is the 2p6, and not like the 3p6, because the difference in energy here is not as large as the distance in energy between, say, these two, or these two, which suggests that they have the same principal quantum number, and they're just different subshells within that shell. The same applies to these peaks. This is a 3s2 and this is a 3p6. Their energy difference between one another is not very different because they have the same n level, but their number of electrons certainly is, because the p holds 6 and the one in the s holds 2. The one orbital in the s, that is. And essentially, what photoelectron spectroscopy has done for us is it has given all of this to us. Not only has it told us that the electrons have ionization energies at discrete levels. By having discrete levels, it's demonstrated that there's various shells and subshells within the atom, and it essentially enhances the quantum model of the atom.
So if we continue to look at photoelectron spectroscopies of particular elements, we can notice a certain amount of similarities and differences between any two given elements. So here we're contrasting scandium, a transition metal, with beryllium, a group 2 alkaline metal. So there's a couple arbitrary differences from these, just resulting from the size of the atoms and other such properties. So if you notice, as the electrons get closer to the core, scandium requires a lot more energy than beryllium to ionize those core electrons. Scandium requires 433 megajoules of energy. These graphs are megajoules, whereas beryllium only requires 11.5 megajoules, and that's because scandium has far more proteins, so the actual amount of energy needed to pry it away from the charge of 21 protons is far more than needed to pry it away from the charge of 4 protons. And if you also notice that scandium has a single emission spectra here at 0.77 megajoules, something unique among all the graphs. The other ones come in even numbers, and this is resulting from the unpaired 3d1 electron that scandium has. In beryllium, all the electrons are paired in the 1s2 and the 2s2, and in scandium they're all paired except for this last one in the 3d1, and so that's where the single emission spectrum comes from. And if you notice, the outermost valence electrons in scandium are slightly easier to ionize than the ones in beryllium. This is because in beryllium they're closer to the core, so there's more attraction there for the outermost electrons, even though there's less protons. So it requires about 0.9 megajoules of energy, whereas in scandium it's farther away despite having more protons, so it only requires about 0.63 megajoules of energy to ionize. But there's also some similarities between these graphs that we can see from looking at them. And in each one, the outer level s electrons are typically ionized very easily in the atoms because of the outermost elements. They only require about 0.63 megajoules and 0.9 megajoules compared to some of the other much higher numbers we see throughout the graph. And the core electrons in each atom are much harder to ionize. Conversely, scandium requires 433 megajoules and beryllium requires 11.5 megajoules. So you can see that in each atom, the core electrons requires a lot of energy to ionize. And also, if you go back quickly just to the relatively low energies on the outside by contrast, the scandium one is lower due to some effects of shielding within the atom. So the electron shields some of that effective charge from the 21 protons, meaning it only requires about 0.63 megajoules as required to 0.9 beryllium, where there's very little electron shielding to protect it from that outside charge level. And an interesting effect that you can see throughout both graphs is that there's about a 10-fold increase in energy level between each N shell. So take, for example, scandium, where you have 0.63 megajoules in the 4s2. When you go to the 3s2, you'll notice about a 10-fold increase to 5.44 megajoules. To the 2s2, 48.5 megajoules, around 50, another 10-fold increase, and up towards 500 in the 1s2 with 433 megajoules. And you can even see this in beryllium, which only has 2 s levels, from 0.9 to 11.5 megajoules. Again, 12 times, so about a 10-fold increase for each level that you see in each atom.
In conclusion, we can say that photoelectron spectroscopy has two main purposes to it. The first being the ability to determine the ionization energy and kinetic energy of electrons and how they come in discrete packets. And secondly, we can also see that photoelectron spectroscopy provides us with a way of determining the molecular and orbital structure of various atoms that have been ionized in the chamber.